Hello and welcome back to AI for Retail Executives. In this lecture, we're going to talk about AI for automating inventory. I think there's been a lot of discussion around different methods here from, RFID historically has promised that customers to collect the out-of-stock data themselves, drones, light sensors, weight pads, robots, shelf cams, shopping cart accessories. We've tried that. And obviously, PI systems, professional inventory systems, computer aided ordering, sales-based predictive ordering, scan in, scan out systems, etc. So there's no shortage of solutions here. We want to talk about all of them, the pros and cons, and what we've seen retailers really adopt and what has worked really well and why. So before we get too much into this, we have to understand what would be the perfect solution. If you could dream up the best solution on the planet, we would have something that would be $0 in cost. It would be 100% accurate in stock, out of stock, low stock, planogram non-compliance, spoiled if it were a fresh product. It would have 0-second delay from when those shelf conditions changed, and it would provide proof to a DSD provider or anyone else and alerts to those folks for them to react to those changes, and no customer or negative customer experience impact. And so nothing that's going to disrupt the customer. So let's put all those down. So like these are all the scores, the scorecard that we're going to put together here. And so we're going to say here first is cost, $0. 100% accuracy, in, out, low, planogram non-compliant, and spoiled. Say if there's other, maybe restock is fine, but if you know in and out, then you know it's when it's restocked. Let's keep adding here. Zoom out a little bit. And we added, we wanted it to be real time. So real time. So when I cause an out of stock, how long does it take my system to react? Provide proof. So some type of like proof system. So I can charge my DSD vendors or what I would like to do if they don't hit the SLA. And then no negative customer experience. Negative customer experience. Let's call it experience. Okay, cool. If there's other pieces there that you really want in a detection solution, let me know. But those are the ones that we have seen before, which have been true. So, all right, let's zoom out a little bit so we can see this. Okay. And so let's go through all the solutions. So we have seen, we're going to leave PI systems to the very end because they're very complex, and to discuss their the pros and cons actually takes a little bit of math, and so we're going to get there. But first, let's talk about robots. So this is your Bossa Nova, your Simbi, these solutions. In those robots, you have a drivetrain, you have a very, very big battery, you have a very high resolution cameras that may be 20 megapixel cameras that each cost about $500, maybe $1,000. You have maybe 2 or 3 computers on board that robot, so that you can do sense and avoid, which is called in robotics, to help make sure you don't hit something. All of that it costs a lot of money. I mean, it's in the orders of like $100,000. If you got those things to scale, maybe it'd be $50,000 robot. And the robot can't go very fast. If it did, it would be unsafe. And so one robot typically can't do more than 1 or 2 passes a day. And so if it's a big Amazon, like a Walmart supercenter, or if it's a big Lowe's, it's gonna. And then there's a bunch of added restrictions and things that you can do to the floor. You cannot put down certain things on the floor, otherwise it will have trouble. Even skylights confuse them sometimes too. So there's a bunch of issues with that. But let's just talk about some of the things that we've just discussed here. So cost, we talked. Yeah, there is a big upfront cost, whether you're paying that or not. Someone has to pay for that robot and ship it across the country. It's expensive to do. So that one's let's give it $3 signs. Let's give it real numbers so we can speak objectively. So I think it's about 100K. And then ongoing, you have typically in every single robotics application I've ever seen in my engineering career, you have a human in the loop when the robot gets confused. And so you're going to have something like per robot, let's say 1/10 of a person, let's say 90% of the time we don't have to man the robot ourselves, but 10% of the time we will. And let's say that person is in Cambodia or the Philippines or India or something like that, and let's say they're at $5 an hour times 12. Let's say the robot is going 17 hours a day, and you're going to have 365 days in a year, and let's just say times 0.1, let's say, and so maybe it's $3,000 or $5,000. Maybe that's a fair number, like 4K every year ongoing. And so the useful life, let's say, of a robot might be 3 years. Maybe that's fair. And so to really get this to a per year, they 33 plus, let's say it's $40,000 a year in COGS might be a fair number. So maybe we'll put this to $40,000. 100% accuracy, in, out, low, NA, planogram non-compliant. A lot of these robots, the only thing it's really doing is it has a depth sensor, which is detecting the depth that it can see on the shelf, and it compares that to the known depth of the shelf. So it's going to look at, hey, if the depth of the shelf is 4 feet, and and I know that and I can see 4 feet right now, then I know there's an out of stock. What's out of stock? It's on the barcode right there. That is what my camera's looking at. And so it's a glorified barcode scanner, and it's going to compare that, and that's how it's going to perform that. The Walmart employees during the COVID detected this, and it was a huge issue. They found they were able to fool the robot just by putting anything blocking or covering the wood, and preventing the robot from detecting the out of stock. And so it didn't really have any product recognition or anything like that. And so it couldn't do this very accurately. It was at like 60, 70% accuracy, or F1 score on in-out, just on in-out. And it did not have low, and it did not have planogram non-compliance or spoiled. So we'll say 70% accuracy there. And then real time, it can only go once a day, maybe twice a day. So I'll give the benefit of the doubt here. The robot can't cover, one robot per store cannot cover a lot. So we'll say 12-hour delay from when an out of stock occurs to when it would be detected again. It does have proof. I'm good with that. It does take images, so it can use those images to show that proof. And no native customer experience. I mean, there's a lot of discussion around this, whether or not people are comfortable with robots roaming the store. And there was, so we'll give this a little minus mark there for not so much. Okay, so that is the robot. Let's talk about the next one. So shopping carts, putting a little sensor on a shopping cart, that was an idea that we pioneered and we thought was a good idea. Shopping cart detector. Our idea was we would have like $100 device that we can put on 50 shopping carts. It would be like $5,000 in total COGS. That would last maybe, and then we'd have to perform a lot of battery swaps. We would have the store do that. So that's, let's say, $10 of labor every week. So maybe it's $40 there times a month times 12, and then we have 5,000 divided by, let's say it lasts for 3 years, and what else? Yeah, let's say that's fine. So that was our original idea, and so we had this. Let's say it was, let's say $5,000 might be a little buffer there, and $5,000 a year in cost. The accuracy, it depended on planogram compliance and things like that, and so we actually had some internal studies. We were at about 80% accuracy. We couldn't get much beyond that because the camera, and what could show what this actual thing looked like. It looked like this. When the camera was close to the shelf, it couldn't see to the top. When it was far away, it could, but it was at a very steep angle. So we would actually get these visual out issues where if the product was recessed at all, we would call it an out of stock, but it's not an out of stock. So the position of your sensor matters a ton, and you could really only get to 80% accuracy with that. So so there's that. Real time, the customer only comes in around 9 o'clock. So if what we actually had is retailers were taking our shopping cart in the mornings and pushing it around, that's not retail automation. And so we were very self-conscious about that. And so, we could bank on average maybe 1 to 2 hours to when a customer would happen to have one of our carts and push it by any specific area. And so maybe say let's say 2 hours delay. Proof, yes, we would have the image. No negative customer experience. Most customers did not notice this thing at all. And so I would say this is like, just maybe just a plus is fine. Okay. And I will say that we pivoted off of this. We went to all of our customers and that had this technology, and in a year prior to us sunsetting the shopping cart detector, we had a convenience store and a home improvement store who was very interested in our technology, but they didn't have any shopping carts. People don't go into a 7-Eleven with a shopping cart typically, but they wanted to detect when out of stocks occurs, in particular in beer. That's a huge out of stock item in most C-stores. And so what we did is we took our exact same pipeline. We made a new sensor called a little shelf cam, a very low cost shelf cam. We'll talk about this shelf cam piece. And we're not going to talk about the cost because, we won't go there. And we were able to solve a lot of the problems that we had with the shopping cart version. So we found that when the sensor isn't moving, so if a camera is moving, it's blurry, and so you get much different, worse images like that. And so if it's fixed on the shelf, you can use a cheaper sensor and get a higher resolution image. All good things. So we actually increase our accuracy. You can position it to be extremely, to avoid the visual out issue to a certain extent, not perfectly. And you can take the image whenever you want. And so your delay could be 10 minutes from when the out of stock occurs. And so we were able to get to 10 minutes, let's say, whatever, anything you want. We can take an image every second if you really want. It just may cost more. So it's possible to realistically get to a 10-minute response time. And then accuracy on in-out NA, we will SLA that we'll get to above 90% F1 score, which is a very aggressive score, let alone maybe 95% and maybe 98% accuracy if you really wanted to use that as the metric. And so we'll say 95% there. And proof, yes, we have the image, and then customers never noticed the small little camera. And so we're, to our knowledge, the only provider of this technology. We have heard that other people have tried to build something similar, but it's very expensive. They're not doing our method at all, and it's very inaccurate. So we've gone head-to-head with other folks who have tried to do this, even with more expensive sensors, and our system was more accurate. So I want to be fair to all different providers, so let's actually keep going and discussing the pros and cons. So there's the next one to discuss are shelf weight pads. And so, one camera just to kind of show this, what we're talking about here. One camera sits on the shelf here, and then takes an image of about 8 feet of shelf, which is 2 mods. So typically it's 2 full mods. I'm not showing my screen. Okay. So one camera, this is a shelf cam, looks across and then sees 2 full mods. And the camera is very inexpensive. And so that's what you can cover. For a weight sensor or any other type of sensor, they're typically on the shelf right there, and they're per SKU. And so the weight pad is typically, let's say about $100. We've heard from PowerShelf, and you need 1 per facing. And so on average per mod, there's about 80 products per facing. And so if you have 80 times, times 2, and it costs $100 per 8-foot section, it will cost $16,000. So it is extremely non-scalable, and I have not seen anyone with their right mind actually go take this very serious. But it is discussed, so we'll include it here. Weight pad, and then if you have so if it's 8,000 a mod. You're going to have, maybe 10 mods per aisle times 2 times 18 aisles. So it'd be like a $2 or $3 million purchase. And let's say it has a 10-year useful life. I don't know. Just divide that by 2, so it's $280,000 per year. And the accuracy, well, a can of Coke weighs exactly the same amount as a can of Sprite, exactly the same amount as a can of Pepsi, exactly the same amount as a can of Minute Maid. It all weighs the same, so it by definition cannot be very accurate. And so I'm going to give this one a 60% accuracy. I'll bet anyone that's going to be on the high end. And it is very responsive. So it's a 0-minute response time. But again, you probably don't want the sensor on all the time. It's going to burn a lot of watts. So let's just call it a 10-minuter, which is probably fine. And then let's see what this is. This is the proof. There is no proof. You could say the weight pad, but DSD will be able to weasel out of that. And then so they could say, well, the weight sensor is faulty. I don't have the image of it. The image of it is unequivocal. You cannot debate that. A sensor reading is tough. No negative customer experience. I'd probably say that's true with this. Okay, cool. So the next one here I wanted to hit was, give me 1 second. Drones. So this has been a topic that we've actually heard that some people are taking very serious. I would highly recommend you do not. Adding a drone into a grocery store, besides the negative customer experience, which is a double negative, I would say there, and the cost. So let's just talk about that. The drone battery typically lasts for about 20 minutes. And so for a drone to fly and actually inspect an area of shelf, likely one drone can only do one side of an aisle. So you would need either you have your choice, either a very low real time to edit, to update the shelf, or from when it would respond to updates in the shelf, or you would have one drone that would take maybe 3 days to scan an entire store. And so I don't know what to put in there. I'll just presume you're going to do that method, and it's going to be something like, I don't know, $10,000 might be fine. And then the ongoing, and $10,000 investment, you 10,000, and then you divide that by 3, and then you add some excess labor or SaaS fee or something. I don't know, maybe it's 500 times 12, so maybe 10K is a fine number to say per month. I'm sorry, per year. The accuracy, I will bet anyone that, and I've worked on some of these problems, a moving camera like that, it cannot be very accurate. It'd be very tough too. And again, if you're using the $10,000 version, you're going to have like a 3-day response time. And then the proof, you will have the image, so that's fine. Let's see. Two other methods here. I will say, so let's see here. We can some of this stuff. If we keep going, we have light sensors on the shelf, and so we have seen these light sensors. I don't know exactly how much these things would cost, but let's say it's just like $10 a facing. I think that would probably be on the low end. And if you had $10 per facing times, like we said, I think maybe there's 30,000 SKUs. So it'd be $300,000 divided by a 3-year useful life. Let's say there's no ongoing, cost there. It was probably still be about 100K, be fair, per year. Accuracy, again, is just detecting if there's anything there or not. So it's pretty easy to fool, the same way with the robots. So I would probably say 70% accuracy again. Response time, very quick. Let's say 10 minutes as well. Proof, no. And negative customer experience, I would say that they wouldn't even notice. So I think that's fine. Okay. Let's discuss RFID. I think this was a highly promised and dramatically underdelivered idea. The main issue is that you have to tag every single product. And so if the average grocery store sells, let's say, 1 million worth of product a week, times this by 52, and the average sales price of a SKU is maybe $5. So there's 10 million products being sold per year, and every single one's going to have a 3-cent tag on it. So that's $312,000 a year. We can get deeper into this, but let's just stop there. And it's still, you have to pay for the antennas, which are not free. So let's just call it $312,000 per year. Accuracy, I think generally it's pretty accurate, but I will say that RFID does not, electromagnetic radiation does not penetrate through liquid and through metal, and so ferrous metals. So you can't, it won't work with in paint cans or soda cans. It won't see through that. It will not detect the RFID tag. It, a bunch of other issues, soda and all that kind of stuff. Campbell's soup, it will not work. So I'll say maybe 70% accuracy as well. And response time quick, let's say 10 minutes again. And, and proof, no. And no negative customer experience. I think that's probably true. All right. So the next one here is customers to collect the out-of-stock data themselves. I am not even going to try to estimate the cost of this. I think it's impractical. You want a very quick response time. Incentivizing customers to do it. Good luck. Try that out. Let me know how effective that actually is. I see zero chance that that's an effective solution that's reliable. In particular, because the same reason that we talked about with a key problem with the out-of-stock detection system on the shopping cart. People wanted this out-of-stock data at 7 a.m. The customers didn't enter the store until 9. And so there was people at 7 a.m. ready to stock, and the system wasn't there, and they could not detect. And so they didn't have real-time, up-to-date information. They couldn't give that data, and so they were pushing around our shopping cart, which is a little bit like putting a broom handle on a Roomba, not really the way it's supposed to be used. So all good there. So let's talk about before we get into the PI systems, these are all the methods that I'm aware of on how to do this outside of perpetual inventory, sales-based predictive type stuff. So drone, weight pads, shelf cams, shopping cart detectors, robots, all these different things. And, I will tell you that the shelf cam is cheaper than all of these options. And has higher accuracy and real-time response, and has proof and has no negative experience. And so after we did this analysis, we basically determined that this is the right answer. We didn't have shelf cams, and we said, okay, let's go bring that to market and we weren't a solution looking for a problem. We actually said, we did this analysis first, and then we said, this is clearly the right answer. We need to be first and the best at this. And so it wasn't tail wagging the dog or anything like that. And this analysis basically allowed us to conclude that this is the right answer. And you can see of these, this is the most accurate, this is the lowest cost, this is the fastest real-time rate, and no negative customer experience, and provides proof. All right, so let's talk about a key competitor of ours, PI, Perpetual Inventory Systems, and some of the issues with them. I think that sometimes people look at, I've heard people say, oh, machine learning can solve this. And so let's actually just define what it is. So if I have my IMS data, so this is coming in real time, I know what IMS believes I have on hand per SKU. Let's say I have my sales data. And let's actually say that I also have IMS and sales data of other stores. And so this is of this store, store 0. And this is store 1, store 2, etc. And so I have a bunch of stores. And so people are trying to take this into account, and they're also trying to take into weather, all these other things into a prediction model that will take all this information over time, all this data here, and then from here predict what's going to happen in the future, some future time, and estimate whether or not I'm in stock or out of stock in a specific SKU. And so it has this baseline, and there's a lot of methods. We'll talk about counterfactual regression, all these different things that you could do to try to estimate this. And let's say that the actual comes in and it's here. Well, if I expect to sell 10 an hour and I sold 0, well, I'll get to statistical significance very quickly to reorder that product, because it's very unlikely that, or I'll check IMS first, obviously, and if that doesn't work, then I'll, if IMS says I have nothing on hand, then you should immediately reorder, and that's very good. To understand these prediction models here, there's many different ways you can do this. The one that you should probably look at is looking at a Poisson distribution. And so when we worked at Apple self-driving car, Apple Maps had this problem to know when a road was closed. And so if you look at GPS data of every single person that has an iPhone driving down a specific road, let's say we'll have 2 roads. One of them is a high traffic, and very high traffic road. If my expected number of cars going down this road per hour is 5, let's say, then I have some distribution that may look like this. Let's say it's a Poisson distribution that looks like this. And so for every hour, and this is 0 cars, 1 car, 2 car, 5 cars, let's say right there, it's 10 cars, then I have some probability that I'll have 0 cars in a specific hour. And so my probability of, and then in the same, let me highlight this example, number of cars per hour equals 100. And so, zoom this down. So what does that look like? So this is 100. This distribution looks like this. There's a much bigger Poisson. And so the probability of 0, that I have 0 cars going down this road at any one time is 0, especially if I kind of take into account slots in time. And so in this one, this high volume, I can predict within 1 hour very confidently, which you can just look at the probability of 0 or close to 0 as being my predictor that this road is closed. Versus, within 1 hour I can predict it very accurately with 100% confidence because it's so high traffic. The road is closed if no one's driving down this road at any one time. In this very slow traffic road, I can't do that. There's let's say that this is a 30% probability that any given hour has 0 cars traveling down this road, even if I take into account time. And let's say 2 in a row, it'd be maybe 0.3 squared. Now it's still, in 2 hours is 9%. And then, multiply it again. So I have 0.3, and let's say I bring that to the power 2, 0.9, 3, in 3 hours, 2.7%, 4 hours, 0.008. So I have 0.8%. It takes me 3 or 4 hours before I can really detect that this is true, that that this road is closed. The same math applies to these predictive models. And so if you're trying to do this per hour or something like that, the average sales for a SKU in grocery per day is 1. And so on probabilistically, there, of course, it's the 80 for the 20, and there's like 5-10% of SKUs you can really do this accurately for. Alternatively, what you have to do is you have to wait for hours before you can actually make a confident prediction about in stock and out of stock. And you can look this up on the Poisson distribution based on the frequency of that product. Saying that you can accurately detect that a product is out of stock based on its sales data without a massive filter lag, is what it's called, is impossible. It violates the laws of information theory. And so, if we go back to these definitions here, the cost for this system is extremely low, and that's why it's attractive. In fact, most of the time, you're going to be able to get a retail or a CPG to pay for your perpetual inventory sales-based prediction, out-of-stock prediction system. The accuracy will never achieve more than 60% if you hold it to make a prediction by the end of every single day. If you allow it to go 3 days, 4 days, 5 days, yeah. But 60% accuracy is not accurate enough. And I have real data on this. We had customers who have built systems internally with very, very sophisticated models that had mispick rates of 25%, meaning that the system said a product was out of stock. Of the things that it said were out of stock, 25% of the time, it wasn't out of stock. And so they were restocking product that was not out of stock. Real time, obviously not. It cannot be. It has to take into account more time to gather more data for it to make that prediction. Proof, no, absolutely not. And negative customer experience, no, it does not have that. But to be fair to this, analysis here, we'll add this one here. %. $0. Let's say it's completely free, and 1 day, and proof, no. Negative customer experience, no negative customer experience. It does have that property, and so this is PI. So those are your choices. As a retailer, you are trying to, we talked about this in the OODA model earlier today. Earlier in the lecture series. to properly observe, orient, decide, act, the first thing you need is very accurate, very real-time data. Having a 1-day delay and having it be only 60% accurate, given that 1-day delay, is insufficient. You cannot run OODA with this. You will always be out of stock. You will always have IMS be inaccurate, and it will cost you massively. It'll show up. The cost will show up in other areas. Inefficiencies in your pick, too slow to reorder. Your ordering will be wrong, and so it is our recommendation that you use accurate shelf cam output, whether it's Focal's or not. Use someone else's. That's fine. That in-stock, out-of-stock data to feed into that PI system and make it even stronger. And it gives it that information that it really needs to make any predictions. Or just use the shelf cam data right out of the box. But once you have that, now you can react. You can run the OODA loop. You have accurate real-time data. You can use that to feed into systems that will, within 10 minutes of Francois going into any store, I can do a shelf scrape and take all the Tide, and it will, within 10 minutes or half an hour, whatever setting you want, it will detect that out of stock. It will rank sort it, add that to the priority queue for that customer or for that associate to restock as quickly as possible if it is a very high moving item. And that is the automated inventory management system of the future for sure. All right, that's all we have today. Thank you so much, and we'll see you in the next lecture.